All right, today we're going to talk about different ways of interpreting graphs of polynomials. Up until this point, you've done linear equations, you've done different parent functions in coordinate algebra and analytic geometry. You did a lot of quadratics and checking that out. Now that we're in advanced algebra, we're going to be doing graphs of polynomials. And polynomials can have all sorts of crazy shapes. They can have ones where both ends point up, both ends point down. They can have lots of different turns and twists in the middle of it. But the basic characteristics stay the same as to what you've been used to seeing. So if we look at number one, basically you have a quadratic equation. It is a parabola. It is flipped upside down. So that it's got a maximum, a highest point, rather than a minimum. But the way that we read the domain is we look at that graph and we see how far to the left can that graph go. Like, would it ever stop? Is there an absolute furthest point, a boundary that makes that graph quit going to the left? So if we look at this graph, and we going to the left of this graph and we trace it, this graph, as we go out to the left, it keeps going and going and going, and really there would be an arrow on the end of this. There is no spot going out here to the left where this graph would ever stop. It would never have like an end point. So if it never stops, then we say that this graph goes out to the left, going to negative infinity. And I'm sure you remember from other classes that a negative infinity just means that it goes into the negative numbers and there's no specific number where it stops. Infinity is not a number, it just means the numbers keep going forever and ever and ever. So if your domain or if your graph never stops, that means it's going to be going towards an infinity. Now, infinity can be positive or negative, and that's going to be depending on which way is it going. If it's going to the left, then we're going to be saying negative infinity. But if we're looking to the right of a graph, then the x values go to positive infinity. So the domain for this one, going to the left, it never stops. Now let's look at the right. As we go out to the right, there's never a value out to the right where this graph is going to stop, where it's going to have an absolute farthest point it's going to reach. So if it keeps going out to the right forever, then we say it goes to positive infinity, because my x values won't ever stop going that way. So the domain for this graph, since it never stops, we would say it goes from negative infinity to positive infinity. Now, whenever we're reading the range of a graph, we're talking about the y values, which means we're looking at how's this graph going to look as we go up and down the y-axis. Now, whenever we're doing the range, we read it from the bottom up every single time. So we got to start from the bottom. So we've got to ask ourselves, if this graph, does it have an absolute lowest point that it goes to? Now, I'm going to add back in our arrows that we had. So we've got our arrows, and they're pointing down. Now, just like we talked about the x-axis, it doesn't just stop at the last number listed on the graph. It keeps going on forever. So the y-axis actually has infinity numbers too. So going down, all the way down, we can extend the y-axis down to a negative infinity and extend the y-axis to a positive infinity. So when we do, I've got to say, what is the absolute lowest point that this graph goes to? Well, I've got an arrow pointing down on both sides. So that means there is no absolute lowest point. There's no minimum value. So if it keeps going down forever, then we say my range is going to go from negative infinity, because there is no lowest point. And then if we trace it all the way up, starting from the bottom, and we trace our graph all the way up. It goes from negative infinity, but there is a point right here that the graph never gets higher than. It's got a maximum value. So that maximum value tells me where the range is going to stop, because your graph never passes that highest value. So that's going to be where my range stops. So for this example, the range is going to go from negative infinity all the way up until this line, which happens to be at the y value of 9. So my range is going to go from negative infinity to 9. And 9 is an exact stopping point. It actually touches that line. So we're going to give it a bracket, because 9 is an exact number and it touches that line. Now, if we're talking about the zeros of a graph, then we're just talking about where does this graph touch the x-axis. Zeros have a lot of different names. They can be called solutions, they can be roots, they can be x-intercepts, but really all they're looking for is where does this thing touch the x-axis. So this graph actually has 2 zeros. This graph touches at the x value of -3, and it touches at the x value of +3. So this graph is going to have 2 zeros. It's got a 0 at -3 and at +3, because you're really just looking at where does this graph touch the x-axis. All right, again, so now we're moving to the y-intercept. Okay, so my y-axis is the one that goes up and down. So my y-intercept, I'm looking for where does this graph actually touch the y-axis. Well, that point happens to be right here, the maximum point where we were looking at for the range anyway. That maximum point, it touches at y equals 9. So my y-intercept is 9. Another way that you could write that point, you could write it as an ordered pair with an x value of 0 and a y value of 9 to give it an exact point. Okay, our next one. This is a cubic function, meaning the degree is 3. I'm sure we've probably seen ones like this in coordinate algebra, but a cubic function doesn't change anything about the rules that we already know. So let's go ahead and draw our arrows so that we can get a better look at what's happening in this graph. So to do the domain, domain is my left and right action. We have to say, does this graph ever stop going to the left? Okay, so if we were to extend this arrow even further, this graph would never stop going out to the left. So think about it, if it is going out to the left, we're going into negative numbers. So if it never stops going out to the left, then it's going to go to negative infinity. And then it's going to keep going out to the right, so it's going out into positive numbers. If we were to extend this arrow, it would go on and on forever. So if we keep going out to the right, then it's going to go to positive infinity. No stopping points on that graph. All right, now we got to switch modes. We got to start looking at the range. Now range is y values every single time. So when we're talking about range, we're talking about what's happening going up and down. So we have to say, does this graph have an absolute lowest value? And does this graph have an absolute highest value? So look at my arrows. Remember the range, we got to start from the bottom up. Every time, start from the bottom. So we got to say, what is the lowest that this thing's going to go? The lowest that this graph's going to go, it's going to keep going down, 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 down. So if it never stops, that means it's going to go to negative infinity. So my range is going to go from negative infinity to, okay, now let's look at the top. Let's see if it ever stops going up. My graph is going up. It's got an arrow. Arrow means it's never going to stop, so it's going to go to positive infinity. So the range is going to go from negative infinity to positive infinity. No stopping point. Now, if you think back to my last example, it did have a stopping point because that graph looked like this. Both of the arrows went in the same direction. It had a point. So that graph is never going to cross. It's like a barrier. But this one doesn't have that. It's got an arrow going down, and it's got an arrow going up. So that means it's never going to stop going up and down. If we're talking about our zeros, remember that's my x-intercepts. Where is it going to touch the x-axis? So let's look here. I see 1. It touches right there, and that's at the point -1, -2, -3. I see another one right here going through the origin, so that would be at 0. And then the last one is just over here. Looks like it goes through at about 2. So this one has 3 zeros, and its zeros are at the points -3, at 0, and at +2. The last thing we got to look at, we got to look for the y-intercept. Where does it touch the y-axis? Okay, remember my y-axis is the one that goes up and down. So if I'm looking at my y-axis, look right here. It goes through right there at the origin. So the y value at the origin is 0. So we would say my y-intercept is at 0. Or if you want to put it as an ordered pair, you would say it's at the origin 0, 0. All right, next problem. All right, this one, if we look at the ends of it, both arrows are actually going to be pointing up. If we were to extend them, on the left it's going up, and on the right it's going up. Okay? Now, they have arrows. There's no stopping points again, and I think you're going to see this as a trend a lot of times. The domain, it's never going to stop going to the left, and it's not stopping going to the right. Even though it looks like it's just going straight up, there's no boundary lines. There's no cutoff points that make it where it's going to stop. So, as long as it's never going to stop going out to the left, we're still going to say it's negative infinity. And going out to the right, we're going to say it's positive infinity. So the domain here is going to be negative infinity to positive infinity. Now the range, remember that's my y values. So we're talking up and down. And when we read the range, we always read it from the bottom up. Okay, so starting at the bottom. The lowest that this graph goes, I've actually got a boundary line down here. This graph never goes below the value at -20. So it's got a minimum. That's as low as it's going to go. So the lowest it's going to go is at -20. That means my range begins at -20. So my range is going to go starting from the bottom, -20. All the way, okay, so then I just trace it up and see, hey, where does it stop going up? My range never stops going up. And if it doesn't have an absolute highest point, then we just call that range, we say it goes to positive infinity. All right, let's talk about zeros. Zeros are my x-intercepts. So we're talking about where does it touch the x-axis. So my zeros, I've got one right here at -3. I got one right here at +3. Now, if we look at it right here, something's happening at the origin, at 0, 0. That's actually what we call a double zero, meaning that the graph comes up, it touches a value, and then it shoots straight down. It doesn't cross over. Like my graph, it doesn't go at 0 and then come back down. No, it's coming up to 0. It touches it here, but then it goes right back down. This actually counts as 2 zeros when it does that. When it comes up, it doesn't cross, and then it just kind of bounces. It's like a bouncing ball. You could have a double zero that looks like this. It could come down, hit the ground, just like a bouncing ball, and then go straight back up. Okay? These are called double zeros. So those actually count as 2 zeros apiece. So when we're listing them, we got to say 0 2 times. So I'm going to say I've got a 0 at -3. I got a 0 at +3. And I got a double zero, so I got one at 0 at 0, because this is where we had the bounds. Now I got to do my y-intercept where it touches the y-axis. So let me get all this out of the way. Looking at my y-axis, here we go. It touches the y-axis right here at 0 also. So that 0 point, that's a pretty important point for us. Or you could also write it as an ordered pair at 0, 0. All right, looking at my next problem, number 4. Now, the first thing that I notice whenever I'm doing this is if I look at my graph, it's coming down, and I look right away, I know I'm going to be dealing with another one of them double zeros in this one. Because, look at my graph, it comes down, it hits, and then it bounces right back up, just like a bouncing ball. Okay, so I know I'm going to be having me a double zero somewhere around there at -3. Okay, if I look out going to my left, my graph would never stop, would it? So if I'm going to say my domain, my x values for this one, my graph never stops going to the left. So my domain, again, is going to be from -infinity to +infinity, because check out this one. Even though it's going down, it's still going out to the right. It didn't stop. Now my range, remember we read the range from bottom up every single time. So if we start from the bottom, the lowest this graph's going to go is to -infinity, because this guy keeps going down forever. So it's going to go from -infinity all the way up. Let's see if it's got a spot where it stops going up. It sure doesn't, because this arrow means it's going to keep going up to +infinity. So this graph's range is from -infinity to +infinity. Now the zeros, like we were talking about, look at where it touches the x-axis. All right. My first one is, I look at it right here. This is where my bounce happens. That's a double zero. So that means I'm going to have 2 zeros at -3. So I've got to list -3 2 times, because it bounces on -3. Then again, it touches the x-axis right here at the origin again. So we would say it's at 0. Last thing we got to look at, we got to say, well, what about my y-intercepts? Where does it touch the y-axis? Well, this graph touches the y-axis right again at the origin, and the y value at the origin is 0. Or you could write it as the ordered pair 0, 0. Right, as we switch modes, this time it doesn't give us a graph. This time we just have an equation. And what we've got to do is we've got to say, we've got to find the number of zeros, we've got to find the y-intercept, and we have to find the domain. So what we got to do to find the number of zeros, my number of zeros is going to be the same as the degree. Now, if you remember, the degree is, goodness, I done pushed something. I'm sorry. 1 second. All right, the degree is the same thing as the biggest exponent. Okay, so if I'm doing the degree of this, that means I'm looking for the biggest exponent in the whole thing. So here's my biggest exponent happens to be this term. And the exponent here is 3. So if my number of zeros tells me I get that from the biggest exponent, then the number of zeros for number 5 is going to be 3 because the biggest exponent is 3, so 3 zeros. Your y-intercept is going to be whatever your constant is, meaning your plain old number. So going back to this equation, my constant, the plain old number without a variable, would be 9. So 9 is going to be the y-intercept. The domain for this graph, we know it's cubic, and we know it's flipped upside down. So my graph's going to look something like this. The domain for this graph, the x values, they never stop going to the left, and they never stop going to the right. So again, and this is going to look mighty familiar. Once again, my domain is from negative infinity to positive infinity. Now let's see if we can use that same stuff as we look over here at number 6. Number 6, I need to look for my zeros, which means I need my biggest exponent. Here's my biggest exponent. It's x to the 4th. So x to the 4th, 4 is going to be my number of zeros. My y-intercept is my constant. So my constant, my plain old number, is going to be 1. So 1 is going to be my y-intercept. And then the degree is quartic. So a graph that is quartic and it has a negative leading coefficient, it looks kind of like the McDonald's arches. So the degree of something like this never stops going to the left. I'm sorry, the domain never stops going to the left, never stops going to the right. So one more time, domain, negative infinity to positive infinity.